Hey everyone, and welcome to This Explainer. I'm really excited you're joining us today because, well, we're going to decode a secret language. We're going to take the messy, super complex physical world of chemistry and discover exactly how it translates into this beautifully elegant mathematical code. It's called chemical graph theory, and honestly, it is absolutely fascinating.
Okay, let's dive right in. Over on the left here, we're looking at physical chemical reality, right? We've got atoms, physical bonds, 3D space, the whole shebang. But here's the catch. Computers don't naturally see physical objects. So what do? We strip all that physical stuff away. Through the magic of abstraction, we get what you see on the right, a pure mathematical network of nodes and edges. It turns out that the messy physical world of molecules actually has this remarkably clean, computable mathematical blueprint. And once we get our hands on that blueprint, we can do some incredible things.
So, here's our game plan for today. We'll start with the blueprint of molecules, build up our translation dictionary, then decode chemical mysteries, check out some real-world applications, and finally, wrap up with the limits of the graph.
All right, section 1. The blueprint of molecules, turning matter into math.
So here is the core premise, anchored by a beautifully simple equation. A molecular graph is defined as G equals V, E. Don't let the math scare you. G is just the molecular graph itself. V is the set of vertices. Think of those as our atoms. And E is the set of edges, which represent the chemical bonds actually connecting them. Think about a simple water molecule, H2O. You've got 3 vertices, 2 hydrogens, 1 oxygen, and they're connected by 2 edges. And, well, that's it. That is the literal foundation of chemical graph theory.
Moving right along to section 2, the translation dictionary, mapping the concepts. You can really think of this next part as our chemical Rosetta Stone. On the left, we've got the concepts a chemist uses every day. And on the right, the exact concepts a mathematician uses. An atom just becomes a vertex. A chemical bond simply becomes an edge. And that entire molecular skeleton that gives a compound its unique shape, that just translates to the graph structure. Oh, and if we run into a chemical ring, mathematically, we just call that a cycle. We are literally doing a direct one-to-one translation of chemistry into computable math.
Now, you might be wondering, why does this translation even matter? Well, it helps us verify reality. In chemistry, we have this idea of valence, basically the natural number of bonds an atom likes to form, like carbon likes to form 4, oxygen prefers 2. Over in graph theory, the equivalent is the degree of vertex, which is just the number of edges attached to a node. And here is the kicker. These two things must match perfectly. If you've got a proposed chemical structure showing a carbon vertex with a mathematical degree of 5, the math instantly flags it. No way, it says. The graph essentially acts as a mathematical checksum. It ensures that our molecular blueprint actually makes sense in the real world.
But let's refine our map just a little bit. A simple line between 2 nodes really only tells us that 2 atoms are connected. But as you probably know, in chemistry, bonds can be single, double, or even triple. To handle this, chemists upgrade to what we call labeled or weighted graphs. Take a look at ethene, for example. It has a double bond right between its carbons, so we just assign a numerical weight to that edge. The equation simply becomes W equals 2. A single bond is 1, a double is 2, a triple is 3. It's an elegant way to preserve the exact chemical reality right inside the mathematical notation.
And this next bit brilliantly illustrates how shapes translate. One of the absolute most important structures in all of chemistry is the ring, kind of like the 6-carbon ring of benzene. While in graph theory, a closed loop like that is called a cycle. So benzene seamlessly maps to a mathematical cycle of length 6, or C6. So why do we care? Because being able to mathematically define these cycles lets us predict massive physical properties. We're talking about predicting a molecule's stability, its overall shape, its reactivity, and yes, even its boiling point.
Let's put this into practice in section 3, decoding chemical mysteries, applying the language.
Okay, get ready, because this is the classic aha moment in organic chemistry. Isomers. Take a look at ethanol and dimethyl ether. If you're just counting up their atoms, they share the exact same molecular formula, C2H6O. 2 carbons, 6 hydrogens, 1 oxygen, done. But out in the real world, they behave completely differently. Why is that? Well, because as their graph skeletons clearly prove, their mathematical networks are entirely different. Ethanol's graph has the oxygen vertex hanging right off the end. But dimethyl ether? Its oxygen vertex is sandwiched right in the middle. The formula is identical, sure, but the graph absolutely proves that the underlying connectivity is completely distinct.
So how on earth do we get a computer to actually read these visual graphs? We use what's called an adjacency matrix. It's basically just a simple grid showing every single atom. If there is a direct bond between two atoms, boom, we put a 1. If there's no direct bond, we put a 0. Looking at our water example here, hydrogen 1 is directly connected to oxygen, so that gets a 1. But hydrogen 1 is not directly connected to hydrogen 2, right? So that's a 0. Just like that, we've taken a visual, physical molecule and turned it into raw, computable data.
And once we have that matrix built, we can calculate something called graph distance. This is simply the smallest number of edges between any two vertices. And let me tell you, this is huge. By calculating these distances and mapping out the branching patterns across the whole matrix, we generate these things called molecular descriptors. Basically, these are single, tidy numbers that summarize the entire complexity of the graph. We can literally compare the mathematical branching number of two totally different fuels and accurately predict which one will boil first without ever having to step foot in a lab to do a physical experiment. It's like magic, but it's math.
All right, moving on to Section 4, Real-World Applications, Molecules to Numbers.
This brings us to a real game changer, the QSAR pipeline. That stands for Quantitative Structure-Activity Relationship. Basically, it's a rapid-fire predictive machine. Step 1. Create the molecular graph. Step 2. Use that matrix we talked about to extract those mathematical descriptors. Step 3. Feed those numbers right into a model to output a predicted property. Will this brand new chemical be toxic? Will it dissolve easily in water? The graph structure gives us the exact math we need to predict the answer.
And you know, this is exactly how modern pharmaceutical researchers actually hunt for new life-saving drugs. They have these massive, sprawling databases filled with millions of compounds, but they don't search through them by name. They search by graph. They're asking the computer things like, hey, find me all the molecules that contain this specific mathematical subgraph. Or, do they share the same cycle? Are the vertices connected in similar ways? If a drug company discovers that a specific molecular shape cures a disease, graph theory lets them hunt down similar shapes almost instantly.
And the best part? It scales up brilliantly. We're not just talking about small drug molecules. Graph theory works for massive plastics and polymers too. A simple linear polymer? That's just a long mathematical path. But a cross-linked polymer? That's a complex, highly tangled mathematical network. By analyzing the density of this graph network, material scientists can literally predict the mechanical stiffness, the elasticity, and the sheer strength of a brand new plastic before a single batch is ever manufactured.
Finally, let's look at Section 5, the limits of the graph. The map is not the territory. Now, we have to be honest here. A basic molecular graph does strip away a lot of physical reality. It tells us perfectly what is connected to what, but it completely misses the 3D shape. Two molecules can actually have the exact same graph, but differ entirely in how they are arranged in 3D space. We call these stereoisomers, and to be frank, simple graph theory really struggles to tell them apart. It also completely misses electron distribution. Take a molecule like benzene. Ordinary graph theory nicely captures its hexagon shape, sure, but it actually takes quantum mechanics to explain the weird, delocalized electron clouds that really give benzene its famous stability.
So, at the end of the day, we are left with a pretty fascinating realization. Chemical graph theory takes physical structures and turns them into highly computable nodes and edges, which lets us build vast databases, identify tricky isomers, and predict complex properties. It truly gives us the ultimate mathematical map of connectivity. But, as we've just seen, it doesn't show us everything. It leaves us pondering a really provocative question. If graph theory gives us the map of connections, what kind of tools are we going to need to fully explore that complex 3D geometry and the quantum territory of the electrons themselves? Well, that is a mystery for our next journey into the quantum realm. Thank you so much for exploring this amazing topic with me today.